Okay, so now I want to take a few series and determine whether they're absolutely convergent, conditionally convergent, or divergent. So kind of a two-part question here. Three-part, I don't know how you want to look at it. So first, considering the series from 0 to infinity of -1 to the n over the square root of n plus 4. So you start at the highest level. So start by checking for absolute convergence. That's just the best way to work through these problems. So here, I'm going to check first, is it absolutely convergent? So when you consider that, you're taking the absolute value of the terms in your sum here. And so your -1 to the n or -1 to the n plus 1 is going to become just 1. Because this is either -1 or +1. Either way, the absolute value is 1. So that means we're looking at this series. Ooh, I almost put 0 to infinity under the equal sign. Okay. So now we think about this series from a blank slate. Okay, what test would I like to apply? And there are a few different tests that you could apply to this series here. I mean, you could do the integral test. I'm going to do limit comparison test. So what I would choose would be limit comparison test with the series 1 over the square root of n, which in other words, that's 1 over n to the 1/2. That says 1/2 there, which is a p series, p equal to 1/2, which is less than 1, so that diverges. So I'm going to do limit comparison test with the divergent p series 1 over n to the 1/2. Notice that if you're wondering, well, why not direct comparison test is quicker when it works? That's the thing. Here I'm adding 4 to the denominator, so that means that these terms are smaller than these terms, and this series diverges. So that's the inconclusive case, or one of the inconclusive cases with direct comparison tests. If your larger series diverges, so the larger series is going off to infinity, smaller series, then I don't know. That's not determined then if that's going to converge or diverge. We don't know. So direct comparison test doesn't play out the way we need it to. That's why I'm using limit comparison test. So if I take the limit as n approaches infinity of the terms in my given series over the terms in my comparison series, and it doesn't really matter which one's on top, which one's on the bottom. Okay, then that's the limit as n approaches infinity of 1 over, I'm going to get rid of some of this explanation here. So we're doing limit comparison test with this series which diverges. I'm going to change markers before the next video. So this is this. Bring this guy up, flip it over, so square root of n over 1. So we could write that under a single square root n over n plus 4. And you are allowed to move the limit underneath the square root here. So the limit of this expression n over n plus 4 is 1, because it's a rational expression with the same degree in the numerator and denominator. Frank, hey, sorry, the dog's chewing something up. Okay, so ratio of the leading coefficients is 1. So this is approaching 1 in the denominator, under the radical. So the limit is equal to the square root of 1, which is 1. When you get a finite number for your limit here, that means that both series have the same behavior. So because we're comparing with a divergent p series here, that means that this series diverges because we got the finite number there. So they both, like I said, have the same behavior. So that means that this series right here diverges by limit comparison test, which means no, the series is not absolutely convergent. If we make the terms, if we take it from an alternating series to just a series that's always positive, turns out that diverges. But remember, when a series alternates, it's more likely to converge. So we have to drop down a level and say, okay, it didn't work out when I made them all positive. But when we did that, we actually made it harder for the series to converge. So let's go back and look at the actual original given series. So since this didn't work out, we check for conditional convergence. So there you're asking yourself, okay, if I had left this series alone, kept the -1 to the n in there, would that have converged? So if I'm looking at this series to deciding how to determine if it converges or diverges, if it's an alternating series, so if you see that -1 to the n or -1 to the n plus 1, then in a lot of cases what you want to do is use the alternating series test. So with that, you check two conditions. First is the limit of the non-alternating part. So in place of -1 to the n, we just put 1 over the square root of n plus 4. Is that 0? And in this case it is, because that's got the form 1 over infinity. So that's going to 0. And is a n plus 1 less than or equal to a n? Well, let's see. In this case, that would be 1 over the square root of n plus 1, if we plus 4, if I replace n with n plus 1. Comparing that with 1 over the square root of n plus 4. Here I've got a bigger denominator, so smaller fraction. So yes, a n plus 1 is less than a n. It is a decreasing sequence. Well, yeah, this is a decreasing sequence. The terms in the series are decreasing. And so, by alternating series test, this series converges. So the answer here is yes. This series is conditionally convergent.